Alright, so today's podcast has to do with specific heat capacity. And specific heat capacity is something you're likely familiar with due to the summertime as opposed to the wintertime. But if you go to the pool, alright, and I know we go to Black Bob Bay, and oftentimes the concrete is just crazy hot, alright, so you're kind of like on tiptoes, kind of hopping up and down, hopping up and down. If you see a puddle, if you put your foot in the puddle, what's true about it? It's usually not near as hot, okay? And this is because water has a high specific heat capacity, alright? So real quick, things that have high specific heat capacities, we just might do an example would be water. What that means is it has a high capacity to store heat, okay? So it has a large capacity or large ability to store heat with little temperature change. So on a hot sunny day, even if you have like a little puddle of water, the sun's beating down on it all day, if you put your foot in it, it doesn't feel that hot. If it's a bigger puddle, it'll feel even less hot. So the amount of water also makes a difference. Things with low heat capacities, in this example we were kind of talking about concrete, but stuff that even has a lower heat capacity would be things like metals. Alright, so metals have very low heat capacities. And so they have a small ability, and everything else is going to be the same. Small ability to store with or with large temperature changes. Okay? And pretty much everything else is the same. So on our stoves, we typically use metal pans because as soon as we're heating that up, if it's an electric stove or a gas stove, we start heating that pan, and what happens? That pan heats up really, really quickly. We put our food in it, it heats really quickly, but we're not making a mess all over our stove, we're making just a mess in our pan. Okay? Because metals, when we heat them, they can't store energy that well, so their temperature changes really, really quickly because they can't store energy. Where water, if we heat it, it takes either a bunch of energy to change its temperature, or its temperature doesn't change because it can store heat so well. So there's an equation which kind of makes sense of this, and this is a nice way to think of this equation. Delta is a sign that we're going to be more familiar with this semester, but delta simply means change, and it looks like a triangle with a bottom. So delta T is change in temperature. Alright? So if we kind of think of this, if we had a bunch of heat, what's going to happen to our temperature? It's going to go up. So these are directly related to each other. If we add heat, and heat is, the unit is Q. Doesn't make much sense, but this is the unit Q, kind of looks like a 9, but heat is Q. So if we add a bunch of heat, temperature changes. However, if we have a lot of something, alright, will its temperature change a lot or a little? So if we have a lot of water and have the same amount of heat, is its temperature change going to be big or small? It's going to be small. So mass is really inversely related to change in temperature. Okay? And the other thing is our heat capacity. Okay, so M is going to represent mass. And then lastly, our heat capacity itself has the symbol C. Why that's C, I don't know. Sometimes it has a little P underneath it. But C stands for specific heat capacity. And again, if something has a high specific heat capacity, such as water, the temperature change is going to be small. It's an inverse relationship. And if it has a small heat capacity, the change will be large. Okay? So we have this equation, and more often than not, we're going to see the equation like this. This is the way I would like you to memorize the equation. Is Q equals MC delta T. Okay? Lastly, the only thing that P means is that this is happening at constant pressure. Alright? And because pretty much everything in general chemistry for sure, actually everything in AP chemistry, it's only if you go to like the really, really high altitudes or really far under sea level does the pressure really change that much on Earth. So we assume pressure is constant, and all that P means is that. So usually we just say Q equals MC delta T. Okay? The last two things in this podcast are heat, okay, and really the sign of heat. Okay? So heat is Q. And if we have a negative Q, that is completely fine. Okay? What that means is our equation, or our reaction, is exothermic. How come? Because it has negative heat. Alright? Why does it have negative heat? because heat is leaving our system, or it's losing that much energy. If we end up with a positive Q, all right, that means that energy is being gained, which in this case would be an endothermic reaction. All right, so the sign of Q is important. It's not always going to be positive, it should not always be negative, but the sign is important. All right? In this sign, the only thing that's going to change it is our delta T. So it's due to delta T. And delta T is simply T final minus T initial. All right? So that is the way we solve change in temperature. It's always the final temperature minus the initial. So exothermic reactions happen whenever our initial is greater than our final, because if we have a small number minus a large number, we get a negative value. Endothermic reactions are always if our final is larger than our initial. Okay, so if something's temperature goes up, it's absorbing heat and it's being endothermic. If something's temperature goes down, it's losing heat and it's exothermic. All right, so that's just a brief introduction to specific heat capacity, and that is it.